coordinate system. So first we're going to play a game called the boat game. And so we're going to play this polar coordinate boat game and ask ourselves, okay, if there is a ship that is sending a distress signal and we need to locate it on our radar, where would this ship happen to be? Well, hopefully we realize that if we start from our positive x-axis and we go 90, looks like these are by 10, 20, 30, 40, 50, 60, 70, 90, every 10 degrees. So 100, 110, 120, 130, 140 degrees, and it's 140 degrees, 15 units out, 15 nautical miles away. Excuse me. We're going to switch this to 140 degrees, 15 nautical miles away, and we've done the trick. Refresh, try it again. All right, now a new ship is sending a distress signal. Where is it located? 90, 100, 110, 120, 130 degrees away, or 130 degrees from 0, and it looks like it is 6 nautical miles away. So that's the idea of polar coordinates. They're used in navigation, and they help you determine where something is located on a polar coordinate grid. So let's talk about the polar coordinate system. We have our good old standard rectangular coordinate system with ordered pairs x, y, where x is the horizontal distance and y is the vertical distance, and the 0, 0, the starting place for this, is called our origin. However, now we want to talk about something called the polar coordinate system. And a point is now of the form r, theta, where r is the directed distance from the pole, and theta is the directed angle counterclockwise from the polar axis. All right, so the pole is very similar to the origin of our xy coordinate plane, Cartesian coordinate plane, and the polar axis would be what the positive x-axis was originally. Remember, we've always started at 0 degrees here, so that's our polar axis, pole and polar axis. So we're going to plot and label some points. So if we want to use r theta, where r is 2 and theta is pi over 6, that means that we find pi over 6 on our coordinate plane and we move r, or 2, in the positive direction. So 2 in the positive direction means we don't cross the pole. And so we're 2 units out at pi over 6. This is the point A. Next, we need to plot the point 4, negative pi over 3. Well, no problem. We know how to handle a negative pi over 3. That means that we're going in the clockwise direction, pi over 3. So if we're coming down here, pi over 3, and then moving 1, 2, 3, 4 in the positive direction, that means that we don't cross the pole. We move outwards, and B is this ordered pair. C is negative 3, 5 pi over 3. So if we're working with pi's over 3's, we're counting 1 pi over 3, 2 pi over 3, 3, 4, 5 pi over 3 in the positive direction, meaning counterclockwise. However, if we move 3 here, we've moved in the positive direction. It's a directed distance, meaning come away from the pole. However, we're going to need to cross the pole and go 1, 2, 3, 1, 2, 3 in the opposite direction. So this is the point negative 3, 5 pi over 3. This is our point C. So anytime you see a negative value for your r, you need to cross the pole and head in the opposite direction. And finally, we see a negative r and a negative theta for point D. So we're going to start by going clockwise, the opposite direction for 3 pi over 4. So 1 pi over 4, 2 pi over 4, 3 pi over 4 would typically get us here on this line. However, because we want to go 5 in the negative direction, we don't get to go 1, 2, 3, 4, 5 out and become here. We need to go the opposite direction following that same line. So 1, 2, 3, 4, 5. This is point D, which is negative 5, negative 3 pi over 4. Or positive 5, positive 3 pi over 4. So now we want to plot the point 3, negative 3 pi over 4, and find 3 additional polar representations of this point. So hopefully it became apparent for you with that last example that we don't have unique points in this coordinate system. It's not a one-to-one mapping, unlike the rectangular coordinate system. You can actually have 3 additional points without doing any rotations around the pole. So if we have the point 3, negative 3 pi over 4, the best way to do this is to actually plot it. So negative 3 pi over 4 says go clockwise, 3 pi over 4, so 1 pi over 4, 2 pi over 4, 3 pi over 4, and then a positive 3 means come from that pole onto that line. And this is the point 3, negative 3 pi over 4. So we want to find 3 additional representations of it. Without having to do any extra loops around the pole, we can get one positive for r and theta. We can get a positive negative, which we already have. We can have a negative positive, and then we can have a negative negative. So those are our 4 possibilities. So let's talk about the positive theta and positive r. And so let's say if we went actually counterclockwise, how far would we go to end up here? So we went 1, 2, 3, 4, 5 pi over 4 in the positive direction, and a positive 3 out. We didn't cross the pole. Now we want to also talk about the negative. So where would we have to go if we wanted to use a negative 3 with some directed angle? And so we'll say, well, if I wanted to do negative 3, that would mean I would have to cross the pole to get there. And that means I need to be on this particular axis or this particular line. And so we're going to say, okay, that means I needed to go a positive pi over 4, but then do a negative 3 to cross the pole. And finally, we need to find the negative negative. So where would we go to get to the opposite place for this so we can cross the pole with a negative value? In other words, if we wanted to go negative direction, clockwise, we need to get all the way over to this place. X marks the spot, and then we can become negative by crossing the pole. So it would be a negative 3 and a negative, how far did we go? Well, 1, 2, 3, 4, 5, 6, 7 pi over 4. And that gets us our 3 additional polar representations of this point. Not unique. All 4 point to the same exact point without having to add 2 pi or subtract 2 pi from it. So when we want to convert between the two, we have a way of going from polar to rectangular and rectangular to polar given one pair of coordinates. Remember, just like we've been talking about all semester long, this is our x distance, here's our y distance, and here's our r. We just are working our way with a good old basic right triangle. And if we're trying to figure out what x is, we would be working with theta and r, and x is the adjacent. So the cosine of theta is the adjacent over the hypotenuse. If I want to solve for that x, lo and behold, x is going to be equal to r times the cosine of theta. It has been this way all semester long. And if I want to solve for y, because the sine of theta is equal to y over r, then r times the sine of theta is going to be equal to our y. So r cosine theta, r sine theta, no big surprise there. And when we're working our way backwards, if we know x and y and we want to find theta, then x and y are given, the opposite and the adjacent. So the tangent of theta is y over x. So if I want to find out what theta is and tangent's in the way, we're going to do the inverse of tangent, or the arctangent. And so theta would be the arctangent of y over x. And when I need to find out what r is the hypotenuse of this right triangle, so r will be the square root of x squared plus y squared. X squared plus y squared is r squared. To solve for r, take the square root. So let's convert this r theta to rectangular coordinates. I need to know what x and y are. Well, x is our cosine of theta, and y is our sine of theta. So negative 3 times the cosine of 3 pi over 2, and negative 3 times the sine of 3 pi over 2. 3 pi over 2 is 270, and so we have the ordered pair on a unit circle of 0 over 1 down. So our cosine of 3 pi over 2 is always cosine and sine on a unit circle, and so the cosine of 3 pi over 2 is 0. We have a negative 3 times 0, and then a negative 3 times a negative 1. So we would get a 0, 3. Let's check and see if that's right. If I plotted negative 3 pi over 2, that means I am going 3 pi over 2 to the 270, but then I have to go opposite across the pole. Does that look like it could be the point 0.03? Absolutely. So these things should land in the normal coordinate system in the same place, same location. You should be able to go work between the two. All right, so let's convert 2, pi to rectangular coordinates. Well, 2 cosine of pi, 2 sine of pi. So if it's 2 cosine of pi, we ask ourselves what would be the cosine of pi, and you can always start high, end high, in the middle be down low. And this is 2 pi, here's pi, just another way of looking at it. Cosine of pi is negative 1, so we'd have a negative 2 here. Let's work with our sine wave. Sine starts in the middle, ends in the middle, in the middle, in the middle. So the sine of pi is 0. 2 times 0 is still 0, so negative 2, 2. Sorry, negative 2, 0. Let's sketch it out in the rectangular coordinate system, or let's sketch it out in the polar coordinate system and see if it appears to be in the same place. So if we went 2 and pi, first we have to get to pi, and then we're going to go 2 arcs out. Is that the point negative 2, 0? Absolutely. Converting negative 3 pi over 4 to rectangular coordinates. Negative 3 cosine of pi over 4, negative 3 sine of pi over 4. From your table of 9, you know the cosine of pi over 4 is the square root of 2 over 2. So negative 3 times the square root of 2 over 2, and negative 3 times the sine of pi over 4 is also the square root of 2 over 2. Get an eraser here and make a mistake, or clear up my mistake. All right. Let's check and see if that makes sense. If I sketch this, I'm going pi over 4 out. However, I have to cross the pole and go 3 in the opposite direction, so 3 arcs away. Does that make sense that that could be a negative 3 squares of 2 over 2, negative 3 squares of 2 over 2? Absolutely. All right, finally, let's convert negative 6, 8 to polar coordinates. So if I were at negative 6, positive 8, I need to know what r and theta are. So r is found by taking the square root of negative 6 squared plus 8 squared. And we'll get a 36 and a 64, which gets us 100. The square root of 100 is 10, so r is 10. We have the r of our theta. So now we need to find theta. Theta is going to be the inverse tangent of 8 over negative 6. However, we have to remember that when we do these problems, our calculator can lie to us. It's assuming, because our tangent is a function, that is going to be in the first or the fourth quadrants. Our point is in the second quadrant. So let's do a second tan of 8 divided by 6. And we get, one more time, let me try that again. In radian mode, degree mode. Doesn't matter which mode you choose to be in. Put it in degree mode so it's more comfortable and familiar. All right, so inverse tangent of 8 divided by 6 tells me I have a 53.1 degree angle, but this isn't a 53.1 degree angle. It is 180 short of a 53.1 degrees short of a 180. So 180 minus that answer is going to give us 126.9 degrees. All right, let's convert negative 1, 1 to polar coordinates. So square root of negative 1 squared plus 1 squared is going to give us our r. So we'll have the square root of 2. And then we need to do a second tan of 1 divided by negative 1, y over x. So we ask ourselves, where's the tangent going to be a negative 1? Sketch it out. Always sketch these out. We want 1 to the left, 1 up, second quadrant again. So it's a 45 degree angle in the second quadrant. That would be a 135, or if you want to be in radians, it's going to be a 3 pi over 4. Converting 1 square root of 3 to polar coordinates, we have square root of 1 squared plus the square root of 3 squared is going to get us the square root of 4, which is 2. So r is 2. And then we ask ourselves, where is the tangent of square root of 3 over 1? And both are positive, so we're in the first quadrant, so that's going to be a 60 degree angle, or a pi over 3. And again, you can sketch these out and ask yourself if that's going to make sense. If I were at 1 square root of 3, I'm 1 to the right, square root of 3 up. Does that look like that could be a 60 degree angle? And about 2 out, and the answer should be yes. That's it for today.